She went by my house.
I'm so sorry.
Okay, so don't forget to bring your canned goods by Friday at noon. Somebody wants to go home a little early.
No. I will not let you.
Well, if you don't bring them by noon, I'm still going out early.
I like that you use the hippie font.
You like that? I like that.
Oh no. Why would you do this to me? I literally don't even know what you're doing.
It's very productive. See, she's got an answer for y'all.
I clearly have no idea.
Because I'm choosing that one at the moment. Four there. We got four there.
Try that.
Did we learn this?
No.
No.
No, I actually think we didn't cover.
I feel like that's the answer.
I guess I could do
First letter of the alphabet.
We had the test and then we had a whole nother test period.
I would have finished things like that. Hopefully about 8. I'll text you, and when the meeting's almost over, I'll be like, hey. Probably gonna go to the library. Yeah, there's anatomy.
Okay, are y'all up there?
Probably not European. What's the
I got 24. So is there 2 people not up there? Okay, we're all there, right? Is that going to jump to 25?
We tried.
Okay. So when you look at that, what's a way to analyze it? Okay, what's the leaving group? Excellent. What else?
Is sodium, or yeah, is the sodium a spectator ion?
Yes. So this would be Na plus and OCH2 CH3 minus. Okay, now what? What do you think happens? Where do these electrons go? To the what?
No, to the carbon with the
All right. And then what happens? Goes bye-bye. Okay? So what's the product? Did anybody pick these?
I really wanted to,
But you decided to go for your 25% shot. I can deal. Okay, so when we've done substitution reactions, we have done the one-step mechanism, which is an SN2 reaction.
I'm so confused.
Okay, the 2 does not mean the number of steps. It means how many molecules are present in the rate determining step. Okay, that's what the 2 stands for. It's bimolecular. Okay, so this is the one that we've done, the first one up here, the one-step mechanism. Well, there is another way that you can do this, and it is a 2-step mechanism, where the halide leaves first, and then the nucleophile comes in. Okay, so notice that this carbon right here has what on it? What is this? Yeah, a plus charge. So what is that called? Carbocation. Yeah, carbocation. That works. Okay. What do you know about carbocations? What? Okay, well, we'll go over it. All right. Which mechanism predominates is dependent on the structure of the alkyl halide. Okay, the reactivity of the nucleophile, the concentration of the nucleophile, and the solvent. Remember we talked about polar protic and polar aprotic? Oh boy. You have a lot to do next week while you're home sleeping and eating, right? Okay.
Oh, we need to go back.
Yeah, can you go back?
That's a lot of words missing.
I didn't even know that was there. Because I made the other one. That's okay. Maybe we'll do better at it this time. It's similar to the other one. Okay, did you get all your words written? So it's structure of the alkyl halide, reactivity of the nucleophile, concentration of the nucleophile, and the solvent in which the reaction is run. Okay. All right, are you with me now? Now, you ready? Remember what we said about how to analyze it? Can you have a what?
What does K mean again?
Potassium.
Oh, okay. I thought it was like R. Sorry. I'm going home now.
I didn't even give you E.
Use it anyways.
But use it anyways. All right, are we all up there? Everybody up there?
Oh, heck yeah.
There we go.
Okay, so what did we do on the last one? We said, what was the, okay, what's the leaving group? Okay, what's the K? Potassium. Okay, what does that have to do with anything? Spectator ion, so you're gonna have, it's not gonna be okay. It's gonna be okay. Honest. Okay, so what is this thing? What is that called? The nucleophile. So where's it going to go?
Right there.
And that goes there. Okay, so what do you get? Okay, make sure you count your carbons, that you draw it correctly. If you have to draw the product, notice there's 1, 2, 3. 1, 2, 3, 4. Okay, these are these 3 up there. Okay, everybody see the 2 pieces? So that later on when I say what nucleophile and alkyl halide would use to make this, you got to know where the pieces are. Okay, so here is T-butyl bromide and water. Okay, we have a sterically hindered alkyl halide and not a very good nucleophile. It still is a nucleophile because remember that water, the oxygen has 2 lone pairs on it, so it can function as a nucleophile, but it's not as strong a nucleophile as OH minus. So they thought when they tried this, they said, oh, this reaction is going to be really slow and it's not even going to work. And they found out that that reaction is 1,000,000 times faster than treating methyl bromide, which would be this one, with water. Okay, it's 1,000,000 times faster than that one. So they said, oh my gosh, we have to go back to the drawing board. Something's not right. Okay, did you have to write all those words down? Are you good? Just a few? Okay, okay, good. All right, so here is the other way that they figured that this would work. And so what happens first is what has to leave this compound? The bromide leaves. Okay, and so we make, this is your next slide, right? Okay. With applause. Plus bromide ion. Okay, now it looks kind of spontaneous, doesn't it? Like she just threw some random arrow up there. Okay, why would it go like that? First of all, when you run these, they're in polar solvent. The polar solvent, bless you, will help to stabilize forming the carbocation and forming the alkyl halide. If you have T-butyl bromide in a bottle, it doesn't just throw bromides off. Okay, right, and sometimes you have to heat them up. Okay, so just so you're aware of that. Okay, then what else was in here besides this? Water, right? Okay, water is going to function as our nucleophile. So how does it do that? So here's the water. I'll just write it over here. I don't know if I left enough spots. Maybe.
You have it written in on the slide.
I have,
Keep going.
oh, okay, okay. All right, so notice that. I'm going to change colors. One of these lone pairs on the O, it doesn't matter which one, is going to go here. Okay, remember that the OH bond is polarized like that. And the lone pair on the O will function as a nucleophile, just like before. So we're going to make a bond between this O and that C. Okay, so what do I have now? I have my T-butyl group, right? Okay, and I have my water. Okay, let me put one lone pair there. Okay, and now I made a bond between the C and the O. Right? Does that look funny to anybody? What's funny about it? The O has how many bonds? 3.
So does one of the hydrogens not like dissociate?
No, no. No, that's like a very small, minute amount of water is dissociated at any given time. There's going to be more water that's just water. You don't kind of like those methyl groups. Okay, so this O is going to have a positive charge on it, right? Everybody see that? Okay, so we have to do something else. Look at the difference between that and the product. What's the difference? One of the H's is gone. Okay, which one in particular? It's a top one, but it doesn't matter. They're both the same. Okay, so how do you think I can get that H off? What else is in there?
Bromine bind to it.
Okay, yeah, you could use bromine.
Or water to bind to it.
Or water. Generally speaking, you use a lot of water, and so there's probably more water in there, but it really doesn't matter. Okay, it's going to be, it's probably both of them are doing it. Okay, so we're going to grab this proton, and these electrons in the OH bond are going to go to the O. That gives us our lone pair up there back. And then we also got HBr. What will happen if HBr reacts with water? You get hydronium ion and bromide ion, right? So that's why it doesn't matter if you use the water to do it, because you would get H3O+. Okay, so I expect you to pick one to be your base, okay? Does that make sense? I want you to pick one. Okay. So don't write both those arrows like that. Okay. How many steps? How many steps do we have right now? 2, 3, 5, 122? Okay. Step 1, make the carbocation. Step 2, nucleophile add. Step 3, deprotonate. Those are your 3 steps. Okay? Sometimes you have that deprotonation step depending on what your nucleophile is. Okay? Okay, when they did the kinetics of this, they found that it didn't matter how much water was in there as far as the rate goes. Okay? If they doubled the amount of water, the rate stayed the same. But when they doubled the amount of alkyl halide, the rate doubled. Okay? So what does that tell you? That tells you that your rate is K times the concentration of alkyl halide. That's your rate law. Okay? And so it's a first order reaction. Okay? So the transition state of the rate determining step only involves the alkyl halide. Now I'm going to go back to that other slide. Okay? I want you to tell me which step up here is the rate determining step.
The first one.
The first one. That means that it's the slow step in the mechanism. Everything else is fast compared to it. It's the rate determining step. Okay? All right. See, that's how they figured that out. Okay, and this was one of their clues to figure out that mechanism. Why would it, could happen that would only involve that T-butyl bromide? Okay. All right, so this is the same reaction except they're using methanol instead of water. Okay, so what do you think is going to happen first? What leaves? The alkyl halide, right? The halogen leaves. Okay, and then what adds? What does this O have on it? 2 lone pairs, so it's going to function as the nucleophile. It's going to add to your carbocation, okay? And then last but not least, we have to deprotonate. When we had water, there were 2 protons to pick from. Now, there's only 1 proton to pick from. Okay? Does that make sense? Okay, so we're going to watch the video of the mechanism. Okay? And then we're going to learn some more stuff about it. Oh. Okay, try that. It says, remember, it's silent. There's no. All right. Be that way. We'll watch it again. All right. So what happened first? That's the bromine leaving. Okay, here's water came in. Now that O is positive. And then another, I'm sorry, methanol came in, and then another methanol removed the proton. Okay, one more time, because I want you to watch that carbon right there. So notice what happened at the beginning when the bromide left. It became flat around that carbon. Okay, do you remember what the hybridization of a carbon in a carbocation is?
Hybridization?
Oh, yeah.
Two.
Uh-huh. And what geometry does that give this? Trigonal who? Planar. Okay, that's trigonal planar. So your molecule has those bulky methyl groups blocking the reactive carbon. So the nucleophile doesn't just come in and do a backside attack because they're in the way. So instead the bromide leaves, It flattens out, and then your nucleophile can come in and make it sp3 hybridized again. This carbon up here is sp3, oops, tetrahedral. I can spell today, maybe. This one is sp2 trigonal planar. That's like really important to note that, because that's going to influence other things in the reaction. Okay, now this reaction, if you were going to do this reaction, the way that you would probably do it is you would just take your T-butyl bromide, dissolve it in methanol, okay, and then collect your that ether that's formed afterwards, that methyl T-butyl ether, okay. When the solvent is also the nucleophile, that is referred to as a solvolysis reaction. Okay, solvolysis is a reaction where the solvent is also the nucleophile. What kind of solvent is methanol? It's polar protic. Okay, what does the polar mean? The charge in the molecule. The electron density in the molecule is skewed. Okay, it's skewed to which atom? The O. Okay, what does the protic mean? It has a hydrogen available for hydrogen bonding. Which hydrogen, there's 4 of them, are available for hydrogen bonding? The one that's on the OH, because that will hydrogen bond to the bromide ion and help stabilize it. Okay, the negative part of the O will help stabilize the T-butyl cation. Okay, and then one of them adds to finish off the reaction. Okay. Okay, so this is an SN1 mechanism. It's a substitution. It still uses a nucleophile, but it's unimolecular. That means there is only one molecule present in the rate determining step. Only one molecule present in the rate determining step. The 1 and the 2 have nothing to do with how many steps, at least not directly. That's the biggest mistake people make and why they get them mixed up. Okay, so here is, this one is the first one that we did where we actually just used water. Which step was the rate determining step? Forming the carbocation. Okay, we're going to draw the reaction coordinate diagram. How many hills will it have? How many steps were there? So how many mountains do we have? 3, 1 for each step. Which one will be the highest mountain? Which is the black diamond? The very first step, right, is the black diamond. All right, so you ready? So we're going to draw it. All right, so here's where we're starting, and here's where we're ending. Okay, so we only have to figure out the middle. That's all. All right, so here we go. Here's where we're starting, and we're going high, right? What do we have here? What did we form in that first step? Yeah, the intermediate, which is the carbocation. So we're going to have, I just love when my finger doesn't work. So we're going to have this. Okay? You still have water, you still have bromide ion. But that's the main thing that's formed. That's your intermediate. Okay, then we're going to go up. Okay, not near as high as the other one. In fact, probably quite a bit lower. Okay, and what do we have down here? What do we get? We had this plus H2O, right? So what did I get here? The OH2 on there, right? That's what we made in the second step. And then what happened in the third step? We removed the hydrogen, okay? That's an easy step. Boy, my little swoopies are kind of sad. Okay, so we have how many steps? So how many transition states do we have? 3. It matches. There's 1 at the top of every one of these. So we're going to draw all 3. Okay. Okay. So here's the transition state for carbocation formation. So we have T-butyl and we have this, I'll just use the eraser. Okay, so what happens in this step? In the first step, we're taking these electrons and we're moving them to the bromine. So what do you think is going to be like the in-between? This bond is doing what? It's breaking. So what we're going to do is make it a partial bond. Okay. What happens to the charge on the carbon in that step? At the beginning, it is neutral. It doesn't have a charge. What happens to it after that step? It is now positive. So in the transition state, we're building up positive charge on that carbon. So it gets a delta plus because the charge is building up. What's happening to the bromine? The beginning, it's neutral. At the end of the step, it's negative. So what are we going to have on the bromine? A delta minus. You see how you figure those out? Look at where you are at the beginning of the step and where you are at the end of the step. Because we have 3 steps, right? Okay, this is the mechanism that you already wrote down. So if you have to look back at that slide, go look back at it. Okay, now what's happening in the next step? We have our carbocation, and what is water doing? It's adding to the carbocation. Okay. Okay, so what bond is forming? The bond between the, oh, that won't stay little. Between the C and the O. This is my bond that's forming. So in the transition state, we're in between. Okay, we're in between. Transition states are in between. Okay, then what does the C have for charges? At the beginning of the step, it is positive, and at the end of the step, it is neutral. So what's in between? We're losing what charge on the carbon? We're losing the plus charge. So you write delta plus. Okay. What happens to the O? At the beginning, it's neutral, and at the end, it's positive. So what are we doing here? We're gaining plus charge. See where the partials are coming from. Okay, look at the start and the end of each step. Okay, that's the nucleophilic attack, the nucleophile adding. Okay, and then because our nucleophile was not negative, we have to do a deprotonation step. Okay, so in that step, go back to what I'm going to draw the intermediate. Okay, what bond is breaking in that step? To the oxygen. Okay, so that is going to be the bond that's breaking Man, you just don't like me. All right, I think I got it. Okay, so that's the bond that's breaking. If you have a bond that's breaking or a bond that's forming, you put the partial bond. Okay, now, what about the charge? What was the charge on the O at the beginning of the step? Positive. What is it at the end? Neutral. So the O is going to get partial positive because it's losing its positive charge. It's gaining electron density in the step. Okay? What is removing the hydrogen? What is doing that? This bond is breaking, but the hydrogen doesn't just fall off. Somebody takes it. So who takes it? Bromine or water? I'll use the water. Okay. What happened? This O is what at the beginning? Neutral. What is it at the end? Positive. So it's going to be partial positive. And that's basically how you do all transition states. Think about where you start and where you end up in that one step. Just that one step. Okay, you do one step at a time. There's a transition state for each step. Okay, you with me? You seem like you're not. You got real quiet. It's always a bad sign. You're making me nervous. All right, so this slide simply shows you the relative rates of SN1 reactions for alkyl bromides with water. Okay, the nucleophile is water. The solvent is water. That's called a solvolysis reaction. Okay, so this one is 1.2, what is that, million? 1.2 million times faster than the primary one. Okay, notice the secondary one is 11.6 because we're getting it. We can still make a carbocation, but it's not as stable as a tertiary carbocation. So who remembers why tertiary carbocations are more stable?
More substituents makes sense.
More substituents help stabilize it through induction and hyperconjugation. Okay, now down here, you see this one? When they did it, the rate was a little bit faster than the primary, and they think that it's because the SN2 reaction kicked in. So that's all that is. Okay. Okay, in SN1 reactions, the tertiary is much better than the secondary, then a primary, and this is on the bottom. And we're going to talk about how you know if it's SN1 or SN2. Okay, the best way is to look at the structure of the alkyl halide. Okay. What? There was? What do I have? Do I have this?
Primary and methyl
I think it's at the bottom.
Yeah. Take away that gray.
Oh, they're so unstable.
Well, do you have the gray thing on the bottom?
Yeah, but that's,
Oh, well.
I don't know, it fell off. The notebook software ate it. The primary and methyl, these are the least reactive because the carbocations are the least stable. Okay. This one is the most stable, and the poor little secondary is in the middle. That resolve it? That might be what, something like that. I don't know why it's not on there. All right, so over here, when you look at the alkyl halides, it's the same as SN2, okay? Because the iodide is the better leaving group. Okay, then the bromide, then the chloride, then the fluoride. Okay, since the nucleophile adds after the rate determining step, its reactivity has no effect on the rate of an SN1 reaction. Okay, as far as the nucleophile goes. Okay, my eyes are watering to beat the band. Okay, identify the alkyl halide that reacts the fastest in an SN1 mechanism. We just talked about it, so I bet you got it. Okay, 1 in 25. Okay, just checking. Okay, yes, it's D. Why did you pick D? Because it's tertiary. That's how come. Tertiary is more reactive in SN1 because the tertiary carbocation is the most stable. Okay. Okay. So here, what is the product of this reaction? Can you figure it out before we do the mechanism? So we know where we're going? How do you figure it out? What is the leaving group? Are you sure? You didn't sound real sure. Iodide. Okay, what is the nucleophile? Be specific. What is it? So does OH add to that compound? Is this the product? Ah, that's not a double bond. Is it this? Yeah, because it's not. Okay, remember that this will add, and then what do you have to do? You have to deprotonate. Remember that when you take alcohols, they don't just dissociate and give you OH minus. Just because you're seeing OH. You only get OH minus when you have water, because you can deprotonate that, or you have NaOH, KOH, LiOH. What's the difference between those and this? The bond to the O is ionic. Here, the bond to from the C to the O is covalent. Okay, covalent. So it doesn't just, you don't get a methyl carbocation. Okay, so what you have over here is not going to be OH. It's going to be what now? Oh, who? Oh, what? Okay, this is real similar to the one that was in the video. All right, so what is the first step in this mechanism? What are we going to do? Iodide's going to leave. Okay, I'll put all the little lone pairs on here. Makes me happy. Simple things in life. Lone pairs. Okay, so those electrons in that bond are going to go to the I. So what do we have now? I'm pretty sure I have space on the next slide to do the rest of it, right? Okay. I was pretty sure that's how I did. Okay. All right, so there you go. That's your clue. So what do I need? Yeah, I need a positive charge. And what else did I make? What happened to the I? It has a negative charge. Okay, so do you notice that in the first part, when we start this step, the overall charge on this molecule is 0. What is the overall charge when you add it up over here? It's still 0. So it should always match. Okay? That make sense? All right, you ready for me to go to the next slide? Or are you just going to accept it at least? Okay, so now I have what? What did I make in that first step? Okay, so what happens in step 2? Remember where we're going. You wrote down that structure, right? Okay, so what have I got? Doesn't matter how you draw it. If you wrote it out nice and pretty, that's just fine. Okay. Oh. Okay, no. All I wanted was another color. Okay, so now what do? I'm going to draw an arrow from the lone pair to the carbocation. Okay, remember that as you draw those arrows, you're always drawing from high electron density to low electron density. All right, so what do I have at the end of step 2? There's your clue. Where did I make a bond? From the C to the O. C to the O. Okay, and what else is attached to that O?
Hydrogen.
Yep, don't forget those. Don't just make everything fall off in one fell swoop. Okay, it's 3 steps. Okay, all right, what else do I need? On the, all right. When you look at these 2 compounds, the 2 that are involved in this mechanism, in this step of the mechanism, I should say, what is the overall charge? What's the charge of this molecule? What's this one? Neutral. 0 plus 1 is plus 1. What is our charge over here? Plus 1. You see how they're still matching? Okay, we're still matching. All right, so what do I have to do now? You know where you're going. What's left to get us there? Right, we're going to deprotonate what? That oxygen. And when we do that, it will no longer have a plus charge. It'll have 2 lone pairs. The lone pair that we're missing is we're going to get it from this bond right here. That for whatever reason doesn't want me to write. This bond right here. Okay. All right, so what am I going to use?
Iodine.
You want to use iodine? Okay. Okay, so it's going to pull off the proton, and what happens to the electrons in this bond? Okay, don't forget that arrow. That's part of it. You got to follow the electrons all the way. Okay, so now what did we make? Well, we should have made the product. Okay, and what else did we make from this? HI. That's probably my phone. Okay. Any questions? See how we're following through. Okay, no. SN2 reactions on tertiary centers.
Yes, my daughter. So there doesn't have to be separate ion.
There doesn't have to be a what? No, there doesn't have to be.
Can you show me where the charge matches on the other side?
Okay, well, what do we have here? We have plus 1 and minus 1. So what does that add up to? 0. And what do we have over here? 0. And I didn't put the lone pairs on the O. Maybe you might like that. Okay. Okie dokie. Okay, now it's interesting that the stereochemistry in this reaction is different than the stereochemistry in the other reaction. When we did an SN2 reaction, we were doing what kind of attack? All the time. Backside. Nucleophile comes in from the back, leaving group leaves from the front. When we do this reaction, we're taking our 3D chiral center, losing the halogen first, and making a carbocation. That carbocation is flat, okay? So because of that, the nucleophile can come in from either side. So you're going to get both of them formed. So if you start with one chiral center, okay, R2 bromobutane, and you do this reaction in water, you're going to get both the S and the R. You're going to get both of them. Because the intermediate is flat, you just screwed up and lost your stereochemistry that you paid big bucks for. So you wouldn't make it that way. You would do it different. You would try to make it go SN2. Okay, so that you could get one chiral center. Okay, but water is not a strong nucleophile. It's a weak nucleophile. That allows the molecule time to make the carbocation and go through the SN1 mechanism. Okay, now sometimes the leaving group can block one side. So here's our compound, and we have a chiral center. We have a leaving group over here. Well, those bromides and iodides, they can be pretty big. So when it leaves, this flattens, but right now the iodide is in the way. Okay, and so it can block it, so that makes the nucleophile want to come in from the other side more often. You will still get both, but you might have an excess of the other one, of the inverted one. Okay, but it's going to be like 60-40. Okay, it's not going to be 98-2. Okay, it's going to be, you're still going to see your racemization. There's a time lag where your halide gets to move around and get into the solvent before this side opens up and a nucleophile can come in here or here, 50-50. That makes sense. Okay. All right, so what is the major product for the reaction below? Okay, I don't want to do that yet. Okay, we'll get to that. We'll go back to it. Maybe we'll do it next time. All right, so here we have our S2 bromobutane, okay, plus water, and we get R and S. This is the one with the inverted configuration, and this is the one with the retain. Just retain just means it's the same, okay? When the leaving group leaves, it can block one of the sides, and that's what this is. This is the water can't come in from that side because the leaving group left over there. Okay, so that's how you can get a little bit excess sometimes of this one. Okay. Okay, now this isn't what I want it to be. All right, so I'm going to insert a blank page.
This is a lot of
A lot of writing?
Everything.
like all the products are not right
Oh, well, I used to use drum.
Well, it takes a minute to draw them right, Wazzy.
Okay. All right, here, write them in. Oh, that wasn't it. This is the one. We'll do that other one. All right, write them in. Write in the R, write in the S. Is that what you're missing? The R and the S? Do you have a blank?
Yep.
You don't even have this?
We have that, but that whole side's gone.
The right side's gone. Right, because you get both. All right, so my question for you is, how can you get only the S? From the R. Was it 2-bromobutane, right? That's what I thought was next. Like, okay, how can you do this and get the S? Okay, and we'll do that. We'll talk about that next time. This is how you switch your mechanism. All right, Wednesday. What are you doing in lab this week?
Final.
Ooh. Good luck. You can do it.
Sorry.
Yeah, it just gets me. No, that's the sound of depression.